Select and determine cryptographic solutions. Welcome to this module on selecting and determining cryptographic solutions. Cryptography is essential for securing data in storage, transmission, and processing. It ensures confidentiality, integrity, authentication, and non-repudiation in information security. In this lesson, we will explore the cryptographic life cycle, different encryption methods, and how public key infrastructure (PKI) strengthens security. Let's get started. Cryptography is the science of securing information by transforming data into an unreadable format using encryption algorithms. Only authorized users with the correct decryption key can access the original data. Organizations use cryptography for these major security functions. Confidentiality prevents unauthorized access to sensitive data. Integrity ensures data is not altered during transmission or storage. Verifies the identity of users and systems. Non-repudiation prevents users from denying they performed a transaction. Now let's look at an example. A customer makes an online payment using their credit card. The transaction details are encrypted using AES-256, ensuring that hackers cannot intercept and read the data while in transit. Here's how to use cryptography effectively. Use strong encryption algorithms like AES and RSA. Implement end-to-end encryption for sensitive data transmission. Rotate encryption keys regularly to prevent compromise. The cryptographic life cycle defines how encryption keys and algorithms are managed throughout their lifespan. Organizations must manage encryption keys and algorithms across these 5 stages. Generation, creating secure cryptographic keys using strong algorithms. Distribution, securely sharing encryption keys with authorized users. Use, applying encryption and decryption processes to protect data. Rotation and revocation, updating or disabling keys to prevent misuse. Destruction, securely deleting old encryption keys to prevent unauthorized access. Here's an example. A company using AES encryption rotates encryption keys every 90 days to ensure continued security. Old keys are securely destroyed to prevent unauthorized decryption of past communications. Here's how to properly manage encryption keys. Use hardware security modules, HSMs, to store encryption keys securely. Implement automatic key rotation policies for critical systems. Regularly audit cryptographic implementations to ensure security compliance. Different cryptographic methods provide various levels of security, performance, and functionality. Organizations must choose the right encryption techniques for their security needs. Symmetric encryption, private key cryptography, uses a single key for both encryption and decryption, making it fast but requiring secure key distribution. Example algorithm, advanced encryption standard A. Best use case, encrypting large amounts of data, e.g. database encryption. Asymmetric encryption, public key cryptography. Uses a public key to encrypt data and a private key to decrypt it, enabling secure communications. Example algorithm, Rav Shamir Adleman. Best use case, secure email communication, digital signatures, and SSL/TLS encryption. Elliptic curve cryptography. Uses shorter keys for the same security strength as RSA, making it more efficient. Best use case, mobile devices, IoT, and blockchain security. Here's an example. A website uses RSA encryption to establish a secure HTTPS connection with visitors. The web browser encrypts data with the public key, and the server decrypts it with its private key. Here's how to choose the right encryption method. Use AES for high-performance encryption of large data sets. Implement RSA or ECC for secure communication and authentication. Regularly evaluate cryptographic standards to defend against evolving threats. Public key infrastructure, PKI, is a framework for managing encryption keys and digital certificates to establish trust in electronic communications. PKI relies on these core components to enable secure communication. Certificate Authority CA issues and validates digital certificates. Registration authority verifies the identity of users requesting certificates. Digital certificates used to authenticate users and encrypt communications. Here's an example. An employee logs into their corporate network using a PKI-based smart card. The smart card contains a digital certificate issued by a trusted CA, ensuring secure authentication. Quantum computers threaten traditional encryption methods, but quantum cryptography aims to counter these threats using new techniques. Quantum key distribution (QKD) uses quantum mechanics to securely exchange encryption keys. Post-quantum cryptography (PQC), developing algorithms resistant to quantum attacks. Here's an example. A government agency invests in post-quantum cryptography to secure sensitive data against future quantum computing threats. Here's how to implement and future-proof cryptographic security. Use PKI for secure authentication and encrypted communication. Monitor quantum cryptography developments to stay ahead of emerging threats. Plan for post-quantum cryptographic transitions as standards evolve. Now, let's summarize what we've learned about selecting cryptographic solutions. Cryptography ensures confidentiality, integrity, authentication, and non-repudiation. The cryptographic life cycle includes key generation, distribution, usage, rotation, and destruction. Symmetric encryption, AES, is used for bulk data encryption, while asymmetric encryption, RSA-ECC, secures communications. PKI enables secure authentication using digital certificates issued by trusted authorities. Quantum cryptography is emerging to counter threats posed by quantum computers. By selecting the right cryptographic solutions, organizations can protect sensitive information, secure communication, and future-proof their data against evolving cyber threats. This concludes our module on selecting and determining cryptographic solutions. Up next, understanding cryptanalytic attacks. Stay secure.